Now it's time to solve the differential equations. Matrix A is given by this 4x4 matrix. So we'd like to calculate eigenvalues. So A minus lambda I, we call the characteristic equation, is given by this equation. We'd like to expand this equation with this law. Then it becomes plus, without this row and lines, you can create the matrix. Okay, then we'd like to expand. Then finally you will get for this equation lambda to the fourth plus a plus c plus 4 omega squares lambda squares plus ac minus b square equals 0. So this equations. This equals 0, exactly equal to this one. So to solve this equation, you should consider lambda square is one variable. So lambda squares plus a plus c plus 4 lambda omega squares lambda squares plus ac minus b square equals 0. Then you can calculate lambda squares equal the lambda is becomes plus minus square root. So we have equation for the lambdas. So we name it lambda sub 1, lambda sub 2, lambda sub 3, lambda sub 4. So we have these 4 eigenvalues. The equations, stability of the solutions. X could be expressed as a sum of these 4 terms. And also y is expressed the sum of the 4 terms with exponential. And the alpha sub j and beta sub j are determined by the initial condition and like initial positions of the particle and the initial velocity of a particles. The general form of the eigenvalue is given by these equations. Plus minus L sub 1 plus I m sub 2. And the L sub 1 and the m sub 1 is a real numbers. And the I is the imaginary numbers. If the L sub 1 is 0, xy has a term of the exponential I m sub 1 t. So this is a correspond to cosine m sub 1 t plus I sine plus minus m sub 1 t. So this is the oscillational terms, meaning this point becomes a stable equilibrium point. If the L sub 1 is not 0, the equation has the exponential plus minus L sub 1 t. If the L sub 1 is positive, the exponential L sub 1 t terms is go to the increasing to the infinity. So we call it this is unstable mode, unstable equilibrium point. So let's find out stability of the equilibrium point. For the case of the collinear point L sub 1, L sub 2, L sub 3, we should calculate b, so second derivative with respect to xy. So y equals 0 at here, so y equals 0. So this is 0. So this means b is 0. At the collinear points, b is always 0. Then we'd like to find out a. For example, L sub 1 point. We could calculate a. So a is gonna be second derivative. So this becomes gm sub 1 minus omega square. Then this part is r sub 1. This part becomes minus r sub 2. then you could get this equation. Then A is negative. So by the way, to calculate, we use y and z is 0. Then we discovered A is a negative quantity. Would you like to calculate the C? C is a second derivative with respect to y. You should substitute Lagrange point. And this is expressed this one. And R sub 1, 2 is always larger. R sub 1, 2 is larger than the R sub 2. So this part becomes positive. So positive times positive becomes positive. We find C is positive. So at the L sub 1s, A is negative, C is positive. Then this part is positive. So this is positive. So if you're considering this quantity with this quantity, so this should be larger than the A plus C plus 4 omega squares. So this means inside this part becomes positive quantity. So we discovered lambda sub 3 and 4 becomes real numbers. Exponential positive. This is the positive square root t. This is unstable mode. L sub 1 is an unstable equilibrium point. Also, we could easily show that at the L sub 2 and L sub 3s, A is negative, C is positive. So because of this ones, actually the L sub 1, L sub 2, L sub 3, unstable equilibrium point. Then we'd like to find the stability of the L sub 4, L sub 5. L sub 4 is located at this point. So x coordinate. So because the distance between the m sub 1 and m sub 2 is r sub 1, 2. So half of this length is expressed r sub 1, 2 over 2. This length is expressed nu r sub 1, 2. So x coordinate is expressed this one. This is equilateral triangle. This is 60 degrees, 60 degrees, 60 degrees. Then it becomes, height becomes a square root 3 over 2 r sub 1, 2. And L sub 5 is a y coordinate, is you should put a negative sign here. Then we'd like to calculate A, B, C's. So I skip the calculations, but you can easily show A, B, C's eigenvalues. We have these 4 values. Lambda sub 1, 2 is always purely imaginary numbers, but lambda sub 3 and 4 is expressed positive, negative omega square root minus 1 plus square root 1 minus 24 nu 1 minus nu over 2. So inside of this quantity is less than 1. So this means if you consider this part, it becomes negative quantities. Then it becomes pure imaginary numbers. So it is a stable mode. But as I explained, this condition is automatically satisfied. But this have to be the positive quantities. So this means 1 minus 27 nu, 1 minus nu is less than 1, of course, but have to be larger than 0. So from these equations, in this situation, lambda sub 1, 2, 3, 4 becomes imaginary numbers, pure imaginary numbers. So first this part. So this means 0, nu, 1. So nu have to be between the 0 and the 1s. And from this part, 1 minus 27 nu, 1 minus nu is larger than 0. So this is 27 nu squares minus 27 nu plus 1 positive. So if you draw the curve, so if this is a y is a function of nu. This is y equal 27 nu squares minus 27 nu plus 1. So this point is 1. So this curve have to be the positive. And also this is 1. This range of the nu is a positive quantities. So this coordinate is 0.0385. This point is a 0.9615. So this means if you consider small nu, when the nu is between the 0 and 0.0385, then L sub 4, L sub 5 is a stable equilibrium point. This is a condition for the stable equilibrium point for the L sub 4 and L sub 5. We discovered the stable condition for the L sub 4, L sub 5. In the case of the Sun-Jupiter systems, nu is a 0.001. So this satisfies the condition for the stability. This is the reason why we discovered so many Trojan asteroids in the Lagrange point L sub 4 and L sub 5. Okay, this is the end of this session.